So multi-objective programming problems or multi-level programming problems and other which involve some multi-criteria. It comes under the preview of multi-criteria optimization. So multi-criteria optimization is a broad domain where multi-objective programming problems, multi-level programming problems, and some extension problems are discussed. So when we talk about multi-criteria optimization or multi-criteria programming problems, so it indicates it is a broad domain where multi-objective programming problems, multi-level programming problems, and their extension problems are studied, right? But in this session, we will only discuss about the multi-objective programming problems, their important characteristics, and their extension problems. So we try to include this session only the introductory part. We will have a brief overview on the multi-objective programming problems, and because we have a audience from different streams, so we try to include this session only the introductory and their extension problem. So theoretical part of related to multi-objective programming problem may be of interest of individual participants, right? So first we start what is the mathematical programming problems, because when we talk about multi-objective programming problems, it comes under the preview of mathematical programming problems. Multi-objective means more than one objective function, conflicting objective function is studied, and we try to find the satisfactory or your optimal solution, near optimal solution of the problem. So mathematical programming problem like operation research is a big domain where we studied the different types of problem, different types of techniques or optimization techniques or mathematical programming problems, some new techniques. So it is all come under the preview of operation research. It is a very big domain. And out of that domain, mathematical programming problems are a separate area where the problems are studied in terms of mathematical formulation, in terms of mathematical programming problems, right? For example, PSO, particle swarm optimization, is not related to the mathematical programming problem because this is a techniques, optimization techniques, but we can use the PSO or some genetic algorithm to solve the mathematical programming problems. So operation research, we have already discussed operation research. Like all scientific research, is based on scientific methodology, which involve formulation of problem, constructing a model, deriving a solution from the model, establishing control over the solution, and putting solution to the work or implement the solution. So this is broad area of operation research. It includes the formulation as well as your constructing a model, then deriving a solution and implementation. So now if we formulate that problem in some mathematical formulation or mathematical programming problems, then it can be studied as a mathematical programming problems. So when these models are formulated in mathematical format, which has objective function, set of constraint and decision variables, that types of programming problems are called as mathematical programming problems. For example, linear programming problem. This is a simplest problem of mathematical programming problem because this problem has objective function, set of constraint and non-negativity restrictions, right? And so this type of models are called the mathematical programming problems. So mathematical programming problem is a broad area where we study the different type of mathematical programming problems. So there are so many extension problems or different type of mathematical programming problems are studies. But the thing is, they have different concept to deal with the optimal solutions. Each and every problem, for example, if you are studying the linear programming problem, the theoretical concept of linear programming problem will not work on non-linear programming problem. So each and every problem has different characteristics, different theoretical concept, and different solution techniques. That is why it is important area. That is why the person who is doing research, they studies different type of problems. Even more and more extension and complex problems are being studied. So these models are defined as mathematical programming models. So I have given some of the mathematical programming problems as this, like linear programming problems. As we all know, it is a simple form of problem, and in this problem we have one objective function which is linear, and we have set of constraints which are also linear, and some non-negativity restriction. Then we have non-linear programming problems also, where objective function is non-linear, or maybe some constraint is non-linear. So it is non-linear programming problem. Non-linear means the relationship between the decision variables is not linear, or we can say that the mathematical expression involves the degree more than one. So that is non-linear programming problem. So linear programming problem is a different problem, and non-linear is a different. So they have different theoretical concept. We cannot combine the concept of LPP into the non-linear. But some of the authors have tried to convert the non-linear programming problem into linear, or some convergence. That is a different issue. Then we have linear fractional programming problem. In case we have objective function in some linear fractional part, it means we have a numerator and denominator in objective function, and both are in linear format. Then that type of problem is said to be linear fractional programming problem. So we have some mathematical examples and models. So you will see what is the difference between the linear programming and linear fractional programming problem. So many research has already been carried out in this area, and people has discovered different techniques to tackle this linear fractional programming problem. But nowadays, I think in PG of some of the university, this has been included as a part of syllabus. Then we come to the multi-objective linear programming problems. Multi-objective programming problem involves we have to optimize more than one completing objective function with respect to the set of constraints and non-negativity restrictions. If your all objective functions are in linear format, then we say multi-objective linear programming problem. So in linear programming problem, we have only single objective function, but multi-objective programming problem consists of more than one conflicting objective functions. Now, in this situation, there are so many techniques have already been developed, and the researchers have given the fuzzy approach and all that. Even nowadays, people are also using some evolutionary techniques to deal with the multi-objective programming problems. So then multi-objective linear fractional programming problems. This is again the extension of multi-objective linear programming problem. Multi-objective linear fractional programming problem means the objective functions in multiple objective functions are in the form of linear fractional. It means each and every objective function has numerator, linear numerator, and linear denominator, subject to the set of constraints. So we can see it is little bit of complex than your multi-objective linear programming problem, because in this case each and every objective function is in fractional form also. So some of the theoretical concept of multi-objective linear programming problem will not work on multi-objective linear fractional programming. So that is the difference. Then some of the authors have tried to convert this fractional part into some non-linear functions. Then they derive some of the theoretical concept, and then new techniques. They apply the techniques to find out the at least satisfactory solution to the problem. Then multi-objective linear plus linear fractional. This is again the extension of this problem. Linear plus linear fractional means the each and every objective function is consists of linear part plus fractional part, right? So it becomes some fractional programming problem. So it is the extension of multi-objective programming problems. Then multi-objective non-linear programming problems. It includes the objective functions are in non-linear form. Each and every objective function is not in linear form. It means the degree of mathematical expression of objective function is more than 1. Then multi-objective non-linear programming are further classified into multi-objective quadratic programming, where objective functions are in the form of some quadratic function, right? And then the different type of techniques are used to find the sum of the satisfactory solution. Then multi-level non-linear. It will be discussed in the later session. So these are the extension of multi-level, multi-objective. Now we come to the linear programming first. As we know, the mathematical expression of linear programming is like this. A is the objective function. You can see this is linear expression. All the variable are in linear form, subject to the constraints B, and each and every constraint is in linear form and non-negativity restrictions. So the problem of determining the decision variables, value of decision variable x1, x2, which optimize A and satisfies B and C is called linear programming problem. Right? So we can also write in matrix notation. If we write this problem in matrix format, so we will have Z is equal to C transpose. C is the cost matrix. As we have already discussed, this is C. And this C is used for the simplex method. In table, we calculate Zj minus Cj. Then Ax is less than equals to B. This is the set of constraint in matrix form. And X is the decision variable matrix. It is greater than 0. So it is the matrix form of linear program. This is linear fractional programming. Before we come to the multi-objective linear programming, we must know what is the linear fractional programming. So in this case, you can see we have a objective function which is in linear fractional format, and so Ax is less than equals to B, maybe equal to, maybe greater than, or maybe less than equals to C. And here we assume that the denominator is positive within feasible region. Within this feasible region, the constraint region, we have to assume that the denominator part is should be non-zero, right? So then, if it becomes 0, it becomes infinity. So our problem will not exist. So in order to define the problem, we define that we have to maximize or minimize this objective function. You can see the objective function in the form of your numerator upon denominator in linear fractional, right? It is just like of a non-linear programming problem. This type of problem can be converted into non-linear program also. But some author has considered this as an individual problem, and they derive different type of solution techniques. So this is linear fractional programming problem. And here we assume that it is very important to note that the denominator is positive. We assume that denominator part should be non-zero in the feasible region, right? जो आप linear programming में feasible region बनाते हैं, उसमें आपका denominator part non-zero होना जरूरी, right? Yes, any questions from Manav Rachna University? Yes, any questions, sir?
No questions, sir.
Okay. Then please connect the Government Engineering College, Bikaner. नो दे आर विजिबल, देख लीजिए आप। हाँ, आरसी खेतान को हेलो।
No questions.
No questions. So yes, how many participants are there present in today's session?
Right now, we are around 4 only. They
Okay.
just other people are coming just right now.
Okay.
Thank you very much.
Okay, and please connect to Marudhar. Is connected nahi. So this is the mathematical expression of linear fractional program. So this is just like an extension problem, but theoretical concept of linear programming differ to the linear fractional programming. Cannot apply directly, but some of the researchers has tried to use numerator function as a separate part and denominator function as a separate part. Then they try to find out some of the satisfactory solution for this problem. Anyway, so now we come to our main part, that is multi-objective linear programming problem. So multi-objective linear programming problem seeks to optimize more than one conflicting objective function of the form of linear form of the form of this fix is equal to zix, where I from 1 to k, and where fi is a linear function, because we have decided that multi-objective linear programming. So each and every objective function is linear function subject to linear constant, and we assume that the set of feasible solution is a convex polyhedron with a finite number of extreme points. That is important. So it is a particular problem where we assume that the feasible solution is a convex polyhedron with finite number of extreme points, where we can check the values of each and every objective functions. This is the simple form of multi-objective program problem with these assumptions. Any questions? Ma'am, any question? Because this is related to your area of research. So see, X is from R. Yes. Yes. So X is the set of variables. Here we assume that your set R is the Euclidean space. X1, X2, X is a vector, and its component may be X1, X2 up to Xn. In general, we assume that capital X denote the set of variables. So domain we will not define, because the person who's working on pure part, they define all the things so that they prove the theorems. But as a applied part, we just say X, capital X denote the set of variables. So any questions from the participant at different nodal centers? Any questions, Dr. Vijay Kumar? Yes, ma'am. Any question?
No questions, sir.
Okay. Now, this is the mathematical expression. As you say, X belongs to Rn. So it is a set of real Euclidean space, and mathematically, this multi-objective linear programming problem are defined like this. We have to maximize or minimize more than one objective function which are conflicting in the nature, and then subject to set of constant where X belongs to Rn, the set of n variables. Ax is equal to less than, equals to, greater than, b, x is greater than 0, and b belongs to Rm. Right? Because we are taking m number of constants, so we have taken b belongs to Rm. And where Zi is equal to Cix, it is in linear form. In matrix form we have written, and from I is equal to 1 to k. C is again a cost matrix, and we assume that S is not phi. It means the feasible region should not be empty set. And other notation have usual meanings. Just like in LPP or in programming problems, we define A is a coefficient matrix, B is a requirement matrix, and all the objective functions are in C multiplied by X. So C is the cost matrix. The same way, but the concept is we have more than one objective functions. That is why it is called the multi-objective programming problem. Now we need to optimize each and every objective function, but it is rarely happens unless until we have a robust technique to deal with that. Yes. So, but different techniques are being applied to find out the satisfactory solution, right? So nowadays people are using different techniques to deal with that. So you can see, it can be seen that multi-objective programming problem is just like a single objective programming problem, except that it has a stack of objective function instead of only one. There is the only difference between the linear programming problem and multi-objective linear programming. Only the difference is there exists more than one objective functions, right? Unless in this lecture we will only introduce what is the multi-objective programming problems, a brief overview, and what are their extension problems, right? So we have different techniques to deal with. Now that people are working on some evolutionary techniques like PSO, and even search methods are also being applied to find some of the satisfactory solution in complex objective functions. People are also using the genetic algorithm, which is being used as a search method to find out some of the satisfactory solution of multi-objective programming problems. So it is a just like single objective, instead of we have a more than one objective function. Otherwise, if you delete this part, multi-objective, it will become linear programming. Multi-objective means more than one objective function exists. Now we have multi-objective linear fractional programming. It is again an extension of this problem, but the theoretical concept of each and every problem is different. We cannot use the concept of multi-objective linear programming problem with into the multi-objective linear fractional programming, because the problem is totally changed mathematically. So the properties and theorems related to that is also changed, right? Then multi-objective linear fractional programming problem seeks to optimize more than one conflicting objective function of the form fix is equal to gi upon hx. It is in fractional form. So you can see it is multi-objective linear fractional. It means objective function are in the form of linear fraction, where gi and hi are linear functions. And here we assume that denominator of each of objective function is non-zero on the feasible set. This is important assumption we need to take before we are defining the multi-objective linear fractional type problems. So we define that the denominator must be non-zero, because when the denominator becomes zero, the problem will not exist. In that case, the problem objective function on each and every point of that feasible give the infinity solution. So the problem will not exist to find a optimal solution. This is mathematical formulation. Mathematically, multi-objective linear fractional programming problem is like this. We have same k number of objective function, same set of constant in linear format, and here we can see A is the coefficient matrix and Z is the objective function, which is in numerator upon denominator format. So some authors also use the CAX plus alpha upon DAX plus beta. They said beta is some quantity which is added in the denominator, and said the denominator is non-zero. So here we also assume, So Ci di belongs to Rn, and for all I from 1 to k, dix is greater than 0. So here we assume that should be positive. And other terms have usual meanings. Each and every term is coefficient, B is requirement, have usual meanings. But the concept is we cannot apply the concept of convex set, or you can see the feasible regions property of linear programming into the multi-objective problems. Multi-objective programming problem, we can check the feasible convexity and concavity. But in this situation, we cannot apply the concept of LPP. Just like in LPP or simplex method, we have fundamental theorem of LPP that if a LPP exists an optimal solution, then it will lie at one of the corner of the extreme corner of the feasible region. But that criteria will not apply in the multi-objective case. Right? So now it becomes difficult to find the optimal solution because a feasible solution consists of infinite number of points. So we can also use the search methods, or we can convert that problem into some different problems where we can use the techniques. So that may be possible. So different researchers, so many works has already been done. Many algorithms, many techniques, many theoretical concepts has been already been derived. But there is no robust algorithm is available which give the direct solution, just like a simplex method is not available. Because of the nature of the problem, even the problem differ from objective function to objective function. So they are using some techniques to find some of the satisfactory solution of the problem. Because as we know, we have more than one objective, so it will not be satisfied at every time. So any questions from your side? Any questions from the participant at different nodal center? No question? Please connect to Government Engineering College, Bikaner. Dr. Deepak? Any questions?
No questions.
Okay. So your participants are not visible?
All are busy. Please just as they are free, they will come.
Okay. So please connect RC खेतान पॉलिटेक्निक. डिस्कनेक्ट हो गया और मरुधर नहीं हुआ है. Okay. So this is the numerical example. We have tried to include this numerical example to show what is the multi-objective linear fractional programming. So we have two objective functions. You can see this is the 5x1 plus 3x2 upon 5x1 plus 3x2 with the assumption that the denominator part is zero, is non-zero in the feasible region set. So this is the simple example of multi-objective linear fractional programming problem. Right? So how we will find out some satisfactory solution. Now we come to some extension of multi-objective linear fractional programming, that is linear plus linear fractional. Linear plus linear fractional means your objective function in the form of some linear function with addition of fractional function. So multi-objective linear plus linear fractional programming problem seeks to optimize more than one objective function of this format. We have objective function into this format. That is the sum of linear function and a quotient function, and where f, g and h are linear functions, and denominator of fractional part of each objective function is non-zero in the feasible set. This is the assumptions we will take for the in case of each and every linear fractional programming, right? So each and every objective function is in this format. This is called the multi-objective linear fractional programming. Linear plus linear fractional programming problems. This is the mathematical format of the problem. You can see it is multi-objective linear plus linear fractional programming problem, and where objective function are in this format: LIX plus CIX plus DIX. Denominator is considered as a positive on your feasible set, and other terms have usual meanings. Yes, any questions from the participant at different nodal center? RC Ketan Polytechnic College. Yes, any questions from the participant at different nodal center? Okay. And then any questions from the participant at Manav Rachna University? Yes, any questions?
Hello.
Yes.
Yes. Achha, sir, can you define what is the CI and what is the DI? How will we select the D? It is fair that D should be greater than 0. But how will we select the D is what is D and what is C?
See, these are the notations in matrix format, and for example, we convert the LPP into matrix form, just like if we objective function are in this format. So we have one example like this. You can see this is the case of multi-objective linear plus linear fractional. So you can see this is your 2x1. So if we convert this into matrix format, it will be 2, 0.
Okay.
Right? And at the same time, this is your D. This is your C. C is your 2 and 6. It is in matrix format.
Okay.
And your D is your 1, 1.
Okay. Can you define with some case and then formulate it?
See, this is the mathematical formulation of the problem. So, just like in LPP, we formulated the problem in LPP. In similar way, if the problem is in that format, in some complex problem is there, where the objective functions are formulated into linear plus linear fractional objective functions, then that type of problems are there.
Yeah, that's why I'm asking. You are dividing equation to equation.
Yes.
2x1 plus 6x and then x1 plus x2. Then why we are dividing this equation from 2x1 to 6x1 to 6x1 plus x1 plus x2 plus 1? Why are we dividing? And one is don't have any variable.
These are the objective functions. Z1 and Z2 are objective functions which are to be maximized. Right? Our objective is to maximize. Yes.
But how are we deciding these are the objective function? By some formulation.
So for that we have particular example, right?
Yes,
for example,
particular case, and what is the way to decide this objective function? I want to know that.
Okay, so see, for example, एक problem है जिसमें 3 factor हैं. Profit, you want to increase your profit, plus your quality of service, and also want to minimize the loss. right? There are three factors. So see, L is your profit, and you want to also increase the quality of service, that is your CX, and you are interested in minimizing your loss, so you have put at the denominator part, right? It has become DX. So if you have problem in such a way, and that problem is formulated into linear plus linear fractional programming problem with multiple objectives, then that type
Can
of
you
problems, yes.
Yes, sir. I understand. Can you suggest some book which have this type of problems?
See, in Google you can find the literature on these problems, but because these are a specific problem, right now it has not been introduced in the curricula of the students, PG students. But if you see the books of operation research, then you, in some of the new books, you will find some of the little literature on linear fractional programming. But still on multi-objective linear fractional programming, it is quite difficult. But you can find the research papers and articles on Google. That is the best way to collect the information about this problem.
Okay, sir. Then you just include the links of that type of problems on Google. Then we will see.
See, in Google there are so many literatures are available. It differs from person to person. For example, I am working on some evolutionary technique to solve this problem. So I will search accordingly, and you people are searching for the basic. So it will be differ from that. So you in Google, if you just type multi-objective linear, so many data will be available, literature will be available. So maybe or may not, if I suggest some link, maybe or may not be useful to you or some other participant. So it is not feasible to write the links of particular literature.
Okay, sir. I will see.
Okay. Any questions from other nodal centers? Any questions from the participant at different nodal centers? Dr. Deepak, any questions from participant?
No question, sir.
Okay. So this is the example, numerical example. So I have included x1 plus x2 plus 1. That is your question. So we can see, we can also define this problem into LXI plus alpha plus your CXI plus beta divided by DXI plus gamma. So alpha, beta, gamma are constant, which can also be introduced in the objective functions. Yeah. In linear programming, if you have, see, if you add the constant in some objective function, so it will not affect the optimal solution. That in general form.
Supposing linear programming, we consider 3x1 plus 2x2 only, because 3 is the profit for variable x1 and 2 is the profit for the variable.
For example,
what is the need?
See, if you have given that there will be always 1 rupees tax on your profit, then you will not add the 1 rupees. It depends upon the problem. If you are given that your profit on first product is 3 rupees and profit on second product is 2 rupees, and there is also 1 rupees discount from or benefit, then you will obviously add, but it will not affect on the optimal solution. That is why in general we will not define the problem in that way, but we can define that problem in this way. Yeah. While calculating the optimal solution, there will not be effect on the constants.
After that, when we get the value of x1 x2, these values in the objective function and then sum of the.
Yes. That is why. So here we have added some constants. So we can add. Now we come to the multi-objective non-linear programming problem. As the your wordings of this problem state, we have multiple objectives, and each and every objective function or some of the objective functions are non-linear in nature. So multi-objective non-linear programming problem seeks to optimize more than one objective function of this format, where f(ix) is non-linear function subject to constants, and here we have taken one assumptions that the set of feasible solution is a convex polyhedron with finite number of extreme points. So if there is a denominator exists and denominator is of each objective function is also non-zero. So if in non-linear case, if denominator is also considered as a non-linear, so if denominator exists, it should be non-zero, right? For example, you want to maximize x1 divided by x2. So denominator is x2. It can be considered as a non-linear programming problem also, as well as linear fractional programming problem, because non-linear is a big domain. So whenever fractional is also, we can include as a part of non-linear. This is the mathematical format of multi-objective non-linear programming problem. So we can see there are k number of constants, and zi are non-linear functions, and other usual other notation have usual meanings, and each and every function is some of the functions or maybe non-linear functions. It is not necessary that each and every objective function be in non-linear format. If some of the functions are in non-linear, then we also say it is a multi-objective non-linear program. Right? Sorry. Now we have taken the specific case of multi-objective non-linear programming problem, that is multi-objective quadratic programming problem. So multi-objective quadratic programming problems are non-linear programming problems having objective functions that contain the linear and quadratic forms. It includes the objective function in some quadratic form. Then we say it is multi-objective quadratic programming problem. Just like this is the mathematical formulation. Here we can see there are k number of objectives, and objective functions are in this format, that is cax plus xt dix. This is quadratic form. So quadratic function has specific properties, convexity and concavity. So people who are working on theoretical part, they derive some of the properties and they include that properties with multiple objective programming problems, right? And they derive some optimality criteria. So these are the notation, mathematical expression of multi-objective programming problem, multi-objective quadratic programming problem. So these are all extension problems. But I already said that the theoretical concept and the techniques differ from one problem to another problem, right? We cannot apply the same technique to linear programming to multi-objective or multi-objective to multi-objective non-linear programming. So each and every problem have different concepts, different techniques are being used. Nowadays people are also using some combination of techniques, hybrid techniques, so that they can find some of the satisfactory solutions, because it is rarely happens to find a compromise optimal solution in some with multi-objective programming problems. So they at least find the satisfactory solution, or compromise optimal solution is also find out. Compromise optimal solution is also an efficient solution, which is based on criteria of decision maker. So many research paper has been published, many concepts has been derived, many techniques has been applied, and many analysis has already been done by the researchers. But in our curricula, our students, they are not familiar with that problems. So I hope in future multi-objective programming problem will be the part of curricula of PG students. So this is about multi-objective quadratic programming problems. This is one of the numerical example of multi-objective quadratic programming problem. Now here we have two objective functions. Even more than two objective function may be there. They are not restrictive only two. But again, if there are more than one, it means it is a multi-objective. So you can see this is Z1 and Z2. And this is your quadratic part. This is quadratic function. And this we can treat as a linear part. Right? And these are the set of constants and subject to non-negativity restriction. So we use the techniques to find the satisfactory solution of this problem. Clear? Any questions? Any query, clarification? Any questions from the participant at different nodal centers? Any questions? Any questions from the participant at different nodal centers? No question. Then please connect to RC Khetan. Any questions from participant at Government RC Khetan Polytechnic College?
No questions, sir.
Okay. Then please connect to Dr. Deepak.
No questions.
Okay. Any questions from CET?
No questions, sir. No questions.
So this is multi-objective quadratic fractional programming problem. Again, it is more complex problem. It can be considered as an extension of the problem. And the problem is the multi-objective quadratic fractional programming is considered in this format. We need to maximize of k objective functions, and each and every objective functions are in quadratic fractional form. So the quadratic part can be written in this format also, and it is also in fractional form. It means we have numerator function as well as denominator function, and subject to constants. Clear? So again, different techniques are being used to find out some solutions, but we can use some search method also, because these are some complex problems. They don't have a unique theoretical concepts. It differ from problem to problem. So it is very difficult to find a robust technique to find out the satisfactory solution of this problem. So now people are using the search method, hybrid of methods, hybrid of techniques. Even nowadays, people are also using the artificial neural network techniques to deal with the multi-objective program problems. So many people are working on this field, and hopefully the overview of this type of problems will help you to identify the area of research, and you can also suggest, you can see the literature available to these problems, and may click some of the idea related to the new techniques. So this is the overview about the different type of multi-objective programming problems. So being a teacher, I must be updated what is the problem. Being a teacher, at least your curricula, besides your curricula, you should also learn the students what are the new area. What if some of the इनमें से किसी के भी माइंड में अगर क्लिक हो जाएगा, तो even that will also be helpful to you also, because the student will give you the ideas, the student will give you the techniques. So we have also one of my students in Bikaner, we have worked on some papers related to this type of problems. So I have developed some techniques. So he was very used to on MATLAB. So I said, why not we construct the MATLAB code on this problem. So jointly we construct the code. So we sent the paper to some of the journals. We said it may not be published. It was uncertain. But after 1.5 years, it was published in good journal. And the same code was copyrighted by us also. So that students is now in Australia. He is pursuing the PhD. He has done the MTech from IIT Kharagpur. So the students from very rural area. He belongs to Barmer, basically, and Barmer is such a area where the necessary facilities are not available. And the student was studying under the scholarship of some societies, social societies. So that was at that level only third year student can give you the ideas, techniques. Now that code is very important. So now we can use that code. Even now we are, in order to give the license to the MATLAB to use that, they will include that code into their packages. Then definitely they will give some amount to us also. So that is the what even students have more energy. They have more courage. They have more because we are a teacher. We have so many other duties are also there, and teacher should also be have some ethics. If you are working with someone, so he or she must be credited. And if a teacher think that I am the super, I know everything, it means he is wrong. He is misguiding himself. Because teaching and learning is a continuous process. Once you stop, it means you are making fool to yourself. And when I was started my career, I was just gentleman like this. So I said I know everything. Even I sit on the same way he is sitting in front of the other. So that was wrong. That was wrong, according to me, because you are expert in good, but you should have some respect to the others, and that respect come from the maturity, not by day one. When you come in that field, after year by year, you will learn that you are not up to 100%. You are only 50% or 20%. You need to learn. So there are some punctuations, there are some ethics which we should also learn. Learn before learning the subject. Learning a subject is a different. And everybody knows everything. Even the peon of our institute also knows. He said, you don't know, I know. I said, okay, you know. हाँ, वो कहते हैं आपको. So we cannot contradict them. We are not here to contradict others. Right? Many experts are coming in our lectures. They said, you know, we know that. Okay, you know. Because learning and teaching is a continuous process. You cannot say that I am 100%. If you are 100%, it means you are zero. If you are zero, if you are 100%, it means you are zero. You are. It means you are good for nothing. See, that is what I want to share with you as a expert, you can say, or as some discussion on this issue. So these are some of the punctuations we should adopt. Even this gentleman is senior to me, Dr. Khagender, right? But he is an expert in that area. I am expert in, because nobody expert in every area. That must be clear in each and every mind. So we should also accept our limitations. अपनी limitations को accept करना ही learning है. So, well, anyway, So multi-objective quadratic fractional programming is just a part of this discussion was on some ethics or punctuation of our teaching. Anyway, any questions from your side, from your participant at different nodal center, they can share with me. Any questions from Bikaner College?
Sir, no question. Actually, this topics looks from research area.
Yes.
We are reading this topic first time. We are
See, this is why the course is advanced operation research. We started from linear programming, then we slowly come to the multi-objective, then we come to multi-level, then we have some software demonstration. On tomorrow we have again elementary game theory. Then day after tomorrow we will have some particle swarm. That is what we have designed this course. So it is not necessary always to we have some elementary things. So it is our duty to update some of the recent advancement in this courses.
okay. Okay, sir.
Okay. So any questions from your participants? So this is the numerical example of quadratic multi-objective quadratic fractional program. So you can see these are the constants, and here if you multiply them, we will have quadratic function. So if you multiply with x3, this x3 with 2x3, so we will have 2x3 square and 20 x3 x4. Right, so we will have quadratic function at numerator as well as on denominator, and we have set of constants. So this is what we have also one example we have considered as an example, and in this example we have not considered the constraint part, because our objective is to understand to each and every participant. So we will not go on some complex part. So we have considered one person Woody wants to simultaneously optimize the objective function. One is of maximize and second is of minimize. Right? Now what the solution will be there which maximize Z1 as well as minimize Z2. Maximization में change कर सकते हैं. Then again, what will be the satisfactory solution which will maximize both the objective function and over some feasible region. So you can see, let us assume that optimal solution using objective Z1. If we consider separately Z1, we will have solution 1500 subject to some constant. Constants are skip for this particular example, and its optimal value is 750. So if we consider this problem, the first objective function as a separate objective function, we will have this solution, and value of objective function is 750. If we put this solution into next objective function, so unfortunately it also has the worst possible value for Z. It is for Z2, it is 600. It means the solution, optimal solution for first objective function is worse to the second objective function. Right? So if we use the objective function separately, on other hand, we get the solution 0, 0. If we want to minimize this Z2 separately, minimize means if we put 0, 0, we will get the minimum value. So it is the optimal solution for the second objective function, but it is the worst solution for the objective function first. Now the question is, how do we resolve these objectives? What will be the solution? That is, this type of case is called the multi-objective programming problems. The objective function must be conflicting. At least one objective function must be conflicting with the others. So this is the multi-objective programming problem, and we have also earlier we used the linear aggregated method, very old method, and in this method we convert the multi-objective programming problem into single objective functions by some weights according to your priority. So where W1, W2 are the relative importance of objective functions. So this is old method and this is not efficient method, because sometimes the priorities will not decided, priorities is not certain, or priorities are not available in advance. So in that case it is difficult. So if you give weight to one to objective function and weight 1/2 objective to second objective function, we will have this. Then this problem is converted into linear programming with the weights to the each and every objective function. So we will have this, and for this particular problem, subject to the constraint, 10, 3, 0 also is the optimal solution. So it has the maximum weighted sum over all feasible solution. This is an example, and we have skipped the constraint part where this calculation is being carried out. So this is only to know what is the concept, what is the problem of multi-objective programming problems. So now we have also the applications of multi-objective programming problems. Like multi-objective, nowadays the problems are very diversifying. Because simple problems are not arises in industries or business or even our educations. More and more objective functions are there. So the application is also high for the multi-objective. For example, I am searching for a job. My objective is to get the good salary, good work conditions, good work facilities. I need facilities also. I need holidays also. I need good work environment. Right. So these are my objectives. Now it is all up to me because to satisfy each and every solution is not possible. We can also find only satisfactory solutions where we somehow achieve these objective functions. So similarly, there are many problems occur in real world which are in multi-objective nature. So decision making problems occur in real worlds are in generally multi-objective, and objectives involved in multi-objective decision making problems are often conflicting and non-commensurable and fuzzy in nature. Nowadays, even how we use the language, it is some fuzzy. It means the language is not. For example, if we say the temperature is cold, so in deterministic case we say the temperature below 10 degrees is cold. But cold, maybe it means 9.9 is not is cold and 10.1 is not cold. So cold world is in fuzzy nature. So that type of situation arises, and that type of problems can be converted into multi-objective programming problems. So multi-objective programming techniques give an easy and efficient approach toward the solution of more complex problems arising in management, defense, government. And the significance of technique may be useful for the economic growth and national development also. Some problems that may be more adequately modeled with are illustrated like this. For example, for an industry or manufacturing company, there are so many objectives. Production planning. We want to maximize total net revenue. We have also objective that we want to minimize net revenue in any period. Some accounts related problem is there. Minimize the back order. We don't need the back orders. And minimize the overtime of the staff. Minimize the finished good inventory. These are 5 objective functions. And also we have a set of constraints. Now what will be the solution? And this problem can be formulated as a multi-objective program. Similarly, capital budgeting problem, maximizing the net present value, capital investment requirement, minimum annual operating expenses, maximum investment in projects, then maximum investment in project related to environmental, because so many constraints are given to the industry. You have to put this budget to environment, this budget to at least and so maximum investment in the project. So we have tried to include some of the problem related to the accounts or manufacturing. Like transportation problem. Yesterday we have talked on traveling salesman problem. So we have only one objective, that we want to minimize the time or total cost, right? But this is not simple. In industry, they have more complex problems. They have different objective functions. They want to minimize the time as well as cost, right? So this transportation problem, like you want to minimize the cost, you want to minimize the average shipping time, maximize the production, and minimize the fuel consumption. Whatever they have this objective function. And then these type of problems can be converted into multi-objectives, and then they will use the different techniques. So this is the table of mathematical formulation of LPP and multi-objective. We start from LPP, then linear fractional. So we have clubbed this problem in tabular form. This is linear fractional programming, as we already discussed about this. And this is multi-objective linear programming. This is multi-objective linear fractional, where objective function are in linear fractional form, this form. So more and more extension problems are there, more and more complex problems are arising, and more techniques are being used. And many research papers has been already available in the net. Now this area is not, we can say, because this area is started in the 1980 century. So more and more publications are available. Now people are trying to use the different hybrid of techniques. So any questions from the participant?
Sir, how would we use this technique in the inventory model? Because in your last slide, you tell me that the back order and the cost of the something like that you're discussing.
Yes.
So how would we apply the practical approach by using this method?
See, by this method we cannot say, but what you can do, you can convert your problem in the form of multi-objective inventory problem, right? In that case, you have more than one objective functions. Like in inventory, your objective is to minimize the inventory, right? If you are interested in minimizing the cost and other factors also, then that type of problem can be formulated as a multi-objective inventory related problem, inventory control problems. But for the solution of that problems, you need to take some of methods, right? For example, I am using some fuzzy or artificial mirrors, then you can use. In that case, your paper will be published in some good journals, because as far as my knowledge is concerned, in inventory, soft computing techniques are not being used. But now people have started in some IIT, Roorkee and Delhi.
Can we solve this technique by the Mathematica or MATLAB software?
No, because direct tools are not available. But analysis part is available, because if direct tools are available, then research is completed, I think. Because it is such a complex problems, and I think in MATLAB only you can solve the linear programming or non-linear programming or some PSO. You can generate the solutions, but there is not available any robust, in my knowledge, robust techniques. Otherwise, once robust technique is available, I think research is completed. Nobody will study the multi-objective because one robust technique is available. But as the nature of this problem, it is very difficult to find. So people use different techniques. Like I am using fuzzy, some people is using neural network, you are using some artificial intelligence, some people are using PSO to find some solutions. So it is all depend upon you. You can use their techniques. Robust technique is not available. अगर linear programming में पता है simplex method से solve कर सकते हैं, then why you will use the other techniques? Research is completed. Nobody is working on LPP because it has been simplex is a very powerful tool. And multi-objective case, because the nature of the problem is so complex, so we need to use the different techniques so to find some satisfactory. That is why people are working on this area. Once a fixed technique will be there, nobody will work.
Because this tools is quite important, I think so, on the inventory model.
Yeah, you can club you can club this in inventory also. Now people have already started this work, and they are using some complex technique also.
Two papers already published on this topic.
Yes. They are available. If you Google this, you will find many papers are available. So these are the multi-objective linear. Any questions from the participant at different nodal centers? Any questions?
No, sir.
Okay. Then Manav Rachna University. Any question, ma'am? Any question?
No questions.
So I conclude my session here. In this session, we have a brief overview on multi-objective programming problems and their related